Now that we've seen where the equation comes from for a damped harmonic oscillator and how to turn that into a system of a system of first order differential equations, let's try to visualize what's going on with Maple. And we're going to use the explore command here in a minute. So I'm going to pull up Maple, and I've already typed in our system of differential equations. You'll notice there's my dy dt is equal to v of t, and dv dt is equal to, I'm just using negative y minus v. So I'm basically pretending like k and m and b, they're all just equal to 1, just to make it easy on myself. And you'll notice that the next thing in my list of things inside the DE plot is the list of the dependent variables, y of t and v of t. And then I have my time, amount of time, which of course shows up on my plot as the length of the curve that we're able to see. So the longer that time is, the more of the curve we'll actually see. And then I've included an initial condition, and you can see the initial condition is just t equals 0, y equals 1, and v equals 1. And I'm giving my y value and my v value, my window settings. I'm going to let my curve be equal to, be a blue curve, so it stands out a little bit better. And I've given a title for the graph itself. So there's a lot of stuff inside the code, but let's see what we get when we click on enter here. Boop, where'd it go? Oh, it doesn't like me. I think it's because I forgot to re-hit my with DE tools at the top. Hold on, let me do that. Okay, so let's try this one again. I just had to go back up to the top and tell DE tools to run. I think it's because I closed down my file earlier. So if I hit enter on this one, takes it a second. Scrolling up, there it is. And so you can see we start at an initial condition of 1, 1, and this looks very different than our undamped harmonic oscillator. Instead of just going around and around and around in circles, this is kind of swooping down and then sort of headed towards what appears to be the origin. Now, what does that mean? Remember, this is not what the harmonic oscillator looks like in reality. We're actually seeing what's happening to the position and what's happening to the velocity over time. So initially, our position is increasing. We have a positive velocity to begin with, but then as the velocity reaches 0, vertical axis is the velocity, as the velocity reaches 0 and starts to become negative, the position starts to decrease. And the position reaches 0 here, which means you're back to the rest position, but then it continues because you've got that momentum that kind of keeps it going, and then because of the damping, it looks like it kind of swirls in towards the center. You might say it sort of spirals in. It's not exactly a spiral, but you get the idea. It's headed towards the center. Now we can do the same thing. I'm going to scroll down. We can do the same thing, but instead of relying on the k and the m and the b to be specific values, we can leave those in there as variables. If I try to hit enter, watch what Maple says. Maple says, well, there's an error. You've got some unknowns, extra unknowns, and I don't know what to do with those. So what I'm going to do, instead of trying to hit enter, I'm going to right-click on this, and one of the options, and whether you're using Maple on a Mac or a PC, one of the options is Explore. And so if you hit Explore, it'll pop up another window here in a second. My Maple's a little slow. And of all these options that are on here, we want to make slider bars for B, K, and M. Everything else we can skip. So I'm going to skip all these others. We don't want any of those to be slider bars. And I'm going to make the values for B, K, and M go between, because they're all positive constants. So let's make B just go from 0 to, I don't know, 4. And we'll do 4.0 so that we get a decimal value inside of our slider, so that's more than just whole numbers. And we'll do the same thing for each one of those slider bars. And we don't have to mess around with anything else. We'll just do that and see what it produces. Now the default on this is going to be a slider, or all the slider bars will be set to 0 once Maple decides to make the graph here. Let's give it a second. So we'll be able to adjust the slider bars on this and make the graph appear and change the values of the spring constant, the mass, and the damping coefficient once it pops up. Well, I actually had to go back in and change it because apparently my computer was freezing up. So I went in and I changed the low end of the Explorer to 0.1 instead of 0. And to be honest, 0 for each one of these would have been really awkward because we'd have 0 divided by 0. And that's probably why Maple was giving me a hard time and just kind of hanging in the system. So this is what it produces as a DE plot with the slider bars. And so you'll notice each one of the slider bars, the default is set to 0.1. And so if I increase the value of B, what I'm basically saying is increase the amount of friction. Now take a look at what's happening to this curve as I slide this slider bar. Now the fact that it doesn't go any further than this is just because we're letting T go from 0 to 15. If I made it go further, a larger time value, it would get further. But notice what's happening. The length of the curve is shortening, but basically the velocity is just dropping straight down to 0, and the position then is just sliding down towards 0. So we're seeing a tremendously large damping coefficient. And so even with an initial velocity, the velocity just tanks like almost immediately, and the position starts to decrease after that. So I'm going to drop this back down to 0.1, and then we'll change what happens if K gets bigger. And remember, K is the role of the spring. How stiff is the spring? And right now, it's not a very stiff spring. So if I increase the stiffness of the spring, make the spring constant bigger and bigger and bigger, you can see we wind up with something that's going and it's the more of these kind of spiralings that it does, that's the official noise that it makes, by the way, the more of these spiralings that it's doing, it's basically the weight or the mass on the spring is going back and forth and back and forth and back and forth and back and forth. It's basically swinging back and forth past the rest position multiple times because it's a really stiff spring. And so as that K gets bigger and bigger, eventually it just jumps right off the graph. But a smaller spring constant means that it's kind of meanders. It takes its time getting back towards the rest position because the spring's not very stiff. And of course, if I make the mass on the spring bigger, what do you think is going to happen? You make a bigger mass on the spring, keeping the same spring constant, the spring damping, the same damping. And sure enough, what happens is you wind up with, it kind of stretches it out in this direction. In other words, that mass is moving with an initial velocity, and so it's got more momentum because it's got more mass. And so the position is going to get further out before it the velocity sort of dies off to 0, and then it starts to fall back in the other direction. And so increasing in this direction, motion in this direction, is basically saying the mass is going further away from its rest position because there's more mass. It's got more momentum, right? And so as mass gets bigger and the spring constant, the damping coefficient get bigger, you can see you can manipulate all three of these to make all kinds of interesting graphs, but they have a set effect size, right? We expect the exact same effect every time. So increasing M kind of stretches it horizontally. Increasing K, you could say it kind of stretches it vertically. And increasing B sort of pulls it towards the center. So that B value either makes it zoom in faster towards the center or zoom in slower towards the center. So it's kind of an interesting thing. You can play around with the B, the K, and the M to your heart's content. And I'll include this as part of the Maple document that I post, so you can play around with the values there. So if we stick with a particular value for B, K, and M, like a value of 1 for everything, we get a particular graph. And if we change our initial condition, instead of 0, 1, 1, we make it 0, 2, 2, it still looks very similar because it's following sort of a parallel curve, right? It's following something that's further out. Remember, 1, 1 would be right here, and so it's going to kind of sweep in. We can add to this another initial condition of 0, 1, 1, and you'll be able to see both curves when I hit enter here. The first one is the 0, 2, 2 that's out there. The second one, they both are headed towards that same equilibrium of the origin where there's 0 position and 0 velocity, but they're headed along two different paths because they're two different initial conditions, which is exactly what we would expect given the existence and uniqueness there, right? And so if you have the patience and the time, you can then use the scene command to see what does this look like with just the y versus t, or if you wanted to, you could do the just the t versus v and get a velocity versus time graph if you wanted to. And then, of course, you can take a look at a 3D plot so you can see what's going on with all of these in 3 dimensions. And when we do that, we're just going to take a look at our standard 0, 1, 1 graph. And when we do that, we see that in 3 dimensions, our curve sort of spirals, but it's like it's sliding down the drain of time, right? It's sort of circling the drain and then headed towards that equilibrium. And so when we kind of line it up so that it's the v versus t, like this, it looks exactly like what we would have predicted up here. But that's only because this graph up here is sort of the shadow of our 3-dimensional graph. So we can see our curve, what it looks like over time, either in terms of the velocity versus time, or if I rotate it the other direction, if I rotate it down like this, we can see what's going on in terms of position versus time, right? So that's one of the nice things about those 3D graphs, is you can use them to see any dimensions that you want, right? Including what we call the phase plane. So the last thing that I'm going to point out here is Maple is capable of finding analytic solutions. And so if we wanted to, we could ask, hey Maple, what is the solution for this system? What does it look like? And if you take a look at what Maple spits out as the solution for the system, I've done some color coding on purpose here. And if you notice, the velocity equation is this part right here. All that's the velocity equation. And then the position equation is this. So notice the solution to this 2 differential equation system is 2 equations. One of them is the position equation, because one of our differential equations was dy dt, and the other is the velocity equation, because it's dv dt. And you're not at all going to be surprised to find out that if you have your position equation and you take its derivative with respect to time, you get exactly this, which is the velocity equation. Now, the reason that I've got the color coding going on will make sense here in a second. What I've basically done is said, hey, look, we've got exponential decay times sinusoidal motion, a sine and a cosine with some constants in there. And that's exactly what we see when we look at this graph. We see decay towards the origin, but in a periodic fashion. So the general solution for our system does exactly what we would expect it to. It has exponential decay, but in a periodic fashion towards the origin. Right? So that's a handy little thing to have. Let's flip back to the notes and we'll fill in a little bit as we go here. So back on this page, if you recall, we started off by presuming what we would see if we just let specific values for k, m, and b. So k, m, and b are parameters. And remember, parameters just means they're user defined. So we can set them to match a situation. So for example, a spring with a constant of 2, in this case, it would be 2 newtons per centimeter or something like that. So it's basically telling me how much force does this spring exert over what given distance. So for every newton, or excuse me, for every centimeter you stretch the spring, it's going to fight you with a force of 2 newtons. You could also say what the mass is. In this case, we'd probably be talking about 3 kilograms or something like that. And then the other unit, or the other parameter, is B, and you could choose any value that you want, but I'll just use 1. And the units for this are going to have to be, if you think back to what the equation was for this, if you remember where B is coming from, B is multiplied by a velocity, and B times velocity has to have the same units as each of these other terms, and they are all force terms. This is mass times acceleration. This is a force due to the spring constant. This is a force due to the damping force. So that means this thing in total, has to have units of force. And so the B units have to be force over velocity units, just using a little unit analysis. And so this might be newtons per meter per second. It's a little weird to say it like that, but this is basically saying for every meter per second of velocity that your mass is undergoing, it's met with a fighting force of 1 newton, right? It's fighting that motion, right? And so we found a couple of things when we did this. We set up our graphs, and we were able to see the spring. I should say the spring's motion. And if we use an initial condition t0, y0, v0, if we do an initial condition of something like 0 to 2, just like our graphs from Maple, then we can see what's going on in a couple of different ways. The first way is to see it in terms of the phase plane. And so if you remember, we had the phase plane. It was y of t in this direction and v of t in this direction. And we had an initial condition that started up at 2, 2. And if you remember, the curve kind of swept down like this, and then it sort of dropped over and sort of went around like this and headed towards the equilibrium. And the curve was moving in that direction. And so this is what the phase plane looks like. And so this is the phase plane graph. So notice when we're looking at the phase plane graph, this is not what we see in reality. This is position versus velocity. And the time axis is actually coming straight up out of that graph. But we could just as easily plot this as a scene graph. And so one of the scene graphs that we graphed was velocity versus time. So for example, our graph started with an initial velocity of 2, so it would have been like this. And if you look at the scene graph for this, the velocity immediately, because of the damping, starts to decrease. And it kind of goes through what looks like sort of slight oscillation until it sort of heads along the axis like that. So this is a different kind of graph altogether. This is a scene graph on a DE plot. So you can produce the scene graph that tells you what's going on with the velocity. But remember, that's not actually what you'd see when you look at the mass. So all you see when you look at the mass is it's sliding back and forth, and it would kind of slow down and head eventually towards the origin, or towards the rest position. And so down on the bottom, you can see here's the other scene that you can produce, which is, of course, the position graph. And so this is position versus time. And we can use this to make predictions, right? So we can use the scene graph to predict or to estimate things like, what's the position when t equals 4? And we'd say, oh, when t equals 4, it looks like the position is right about here. So, I don't know, given the scale, you might say that looks like maybe 0.25. But it's negative because it's below the axis. So the position would be negative 0.25, whatever the units are that we're dealing with for position. So we can use these graphs to make position predictions or velocity predictions. We can use them to get a sense of qualitatively what's going on. And the other thing that we can do is make a prediction that as t approaches infinity, which is saying basically what happens to the graph as we look in that direction, you can see that y is approaching 0. That means the position is approaching rest, right? It's headed towards the equilibrium. Now notice I say it's headed towards equilibrium because mathematically it never really gets there, even though you and I both know that the mass is eventually going to come to rest, right? So the mathematical model works, but it's not exactly what we see in reality. So that gets us to the end of this video. We're going to take a look at this same situation for one more page. We got one more video to do where we're going to look at the analytic method for finding a solution.